Okay, in this video we're going to learn how to recognize when angular momentum is conserved and do some examples of problems where the angular momentum is conserved. Now, we learned the definition of angular momentum in the previous video. It was L equals I omega for solid objects and L equals R cross P for point masses. And we also learned that torque, the net torque on a system, equals the time derivative of its angular momentum. And so that means that if the net torque is 0, then the angular momentum of that system will not change, will be conserved. Now, the important thing to note is that it's only about a particular axis that L is going to be conserved most of the time. And that axis is usually going to be pretty obvious from the problem. But the idea is you want to pick the axis such that the net torque equals 0. So let's say that you have a wheel rotating on an axle. So wheels rotating on the axle. Now if we pick the, actually that's a poor example, but if you pick the pivot to be the center, you've got the normal force from the axle and the weight of the wheel, and notice that neither one of them exerts any torque. But now, if you move the pivot over here, you'll find a torque from both of them. The net torque is still 0, so that's not such a great example, but it is usually important to pick your axis. And on some of the more complicated examples, I'll explain how to do that. Now in this example, this first one, relatively straightforward. There's a picture in your textbook, it's problem 45, chapter 12. You've got a model train track that's mounted on a large wheel, free to turn with negligible friction, blah, 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 radius r. We'll treat it as a hoop of radius r, which means that its moment of inertia is mr squared. Look that up on page 227. And it's mounted on frictionless bearings about the center. Now the idea is there's a small train sitting on it, and that train is going to start to move and come to a speed v relative to the wheel. And as a result of that, the wheel is going to start rotating with angular speed omega, and what we want to do is find that angular speed omega. So the first thing we say is, okay, let's find the angular momentum of the wheel. It's just I omega, which is mr squared omega. That's pretty straightforward. Now the angular momentum of the train is going to be its mass times its speed relative to the room times r, because we're treating it as a point mass. Now here's the catch. This speed v that's given is the speed relative to the track. But if you notice a point on the track, that's moving backwards at a speed omega r, and so the speed of the train relative to the room is it's v minus omega r. And the whole angular momentum of the train is negative because it's rotating the opposite direction of the wheel. Now the other thing, we can say that the total angular momentum at the beginning has to be 0, because initially the system was not moving. Now notice that there are torques. The train exerts a torque on the wheel, which makes the wheel spin. But that's an internal torque. And so the sum of the external torques is equal to 0. The train and the wheel exert torques on each other, just like they exert forces on each other, but the net external torque on the system is 0. And so you add all this up, so L total equals 0. That's mr squared omega minus mrv plus little mr squared omega equals 0. And if we solve for omega, it's a fair bit of algebra that I encourage you to work through, not a lot, but it works out to be mv over big M plus little m times r. And that is how you do that particular problem. And now this is one of everyone's favorite physics demonstrations, the ice skater pulling his or her arms in, which we can simulate by having a rotating turntable and a person standing on that. They spin, they pull their arms in, and we notice that they speed up. And this is actually a very, very interesting example. So the first thing to notice is when the arms are pulled in, what's happening is you're drawing mass closer to your body, closer to the axis of rotation. And that means that the moment of inertia decreases. Now, for an ice skater, the torque is very nearly 0, and so that means L is conserved, and L equals I omega. Well, if I is decreasing, that means omega increases. And that's cool. But it gets even better. Now, if you look at the rotational kinetic energy, that's 1/2 I omega squared. And if we calculate the kinetic energy before and after, you'll notice I is decreasing and omega is increasing. But omega is squared. And so the net result is that as the skater pulls his arms in, the kinetic energy increases as the arms are pulled in. Now, where did that extra energy come from? That's the big question. And I'll let you puzzle that out. We'll talk about it in class tomorrow. Also in class tomorrow, I will check questions 9 and 10. Next video, we'll be working a much more difficult example that is just as difficult as anything you're going to see on the AP exam.